You are listening to the Vocal Technologist. Spoken tech for your ears.
Welcome. Today, we're really jumping across the tech landscape. I mean, from the absolute basics, the real foundations of web dev,
Right.
all the way up to, well, the pretty wild stuff happening with AI agents and how they're being built.
Yeah, it's a huge range. And honestly, it feels necessary right now. There's so much focus on the new shiny things like generative AI, but it all falls apart if the basics aren't solid.
Yeah.
So I think today is about nailing those fundamentals, the things maybe we've forgotten, but also getting our heads around these new complex AI challenges.
Absolutely. It's like mastering the old rules and figuring out the new ones simultaneously. Maybe think of it as Tech Tuesdays, but, amplified. If you're tuning into the Vocal Technologist expecting just one thing, well, think again.
Yeah.
We're going to talk about why sometimes the simplest HTML is actually the smartest move, how JSON can, well, quietly mess up your data.
Oh, yeah, the numbers thing.
Yep. Exactly. And this idea of comprehension debt with AI code, that one's got me thinking. So let's dive in, starting right down at the web dev bedrock. Okay, CSS, everyone's favorite puzzle. Let's talk specificity. It causes so much grief. If I've got, say, 5 different rules pointing at the same button, how does the browser actually decide which one wins? What's the logic?
Right, it's the specificity algorithm. And yeah, developers burn hours on this, but understanding the scoring helps. It's basically 3 columns: ID, class, type. Inky ID, class, type.
Okay, ID, class type. And IDs are the heavy hitters, right? Highest score.
Yep, and ID gives you a score of 100. Classes, attributes, pseudo-classes, those are 010, and then type selectors like div or p, and pseudo-elements, they're the lowest at 001.
So 100 beats 010, which beats 001. Simple enough. But what's the real takeaway there? Beyond just the numbers, why does it matter practically?
Well, the takeaway isn't just the score, it's the implication. That 100 for an ID, it's super powerful, yeah, but it's often a maintenance nightmare down the road.
How so?
Because it's so dominant. If you use an ID selector, the next person who needs to override that style often feels forced to use another ID, or worse.
Oh, no, don't say it.
Tom important, yeah. It's like using a sledgehammer for a small nail. The goal should really be to use the least specific selector that still does the job. Keep things flexible.
That makes sense. Less brute force, more finesse. Okay, moving from that kind of specificity to, well, simplicity itself. There's a growing feeling, isn't there, that front-end development has gotten maybe a bit overcooked.
Definitely. Unnecessarily complex is a good way to put it. We see teams pulling in massive JavaScript libraries, hundreds of files sometimes, just to recreate stuff the browser already does perfectly well on its own. It's this normalization of dependency bloat.
So give us an example. What's a case where plain old HTML shines, where we don't need all that JavaScript complexity?
Oh, the details and summary elements are just perfect examples. You use those 2 tags together and boom, you have a fully working, accessible accordion. Click to open, click to close.
No JavaScript at all.
0. None. And yet, how many projects pull in a hefty component library just for an accordion? It's kind of crazy when you think about it. It comes back to respecting the platform, using what's already there, minimize those dependencies first.
Right, use the native tools. That philosophy, it kind of leads into CSS units too, doesn't it? We always had that debate. Fixed pixels, PX, versus relative units like M or rem. Is that still the main choice?
Well, the conversation's evolved. It's less about either now and more about both hand. Modern CSS gives us tools like comparison functions, min, max, and math functions, calc.
Okay, so you can actually combine different units like mixed pixels and rems in the same rule.
Exactly. You can use calc to say barm plus 10 pixels, or use clamp to say bwarm, but no smaller than 12 px and no larger than 18 px.
What's the real advantage of doing that math right there in the CSS?
It lets you build interfaces that are responsive in a much richer way. You can respect the design's intended look and feel the pixel-perfect aspect, maybe while also respecting the user's preferences.
Like if the user bumps up their default browser font size.
Precisely. Your layout adapts gracefully based on their settings and the screen size, not just one or the other. It's more comprehensive responsiveness.
Okay, that idea of respecting the platform, minimizing dependencies, it links nicely to something potentially more dangerous: data integrity. We just talked about respecting user input with clever CSS, but what about respecting the data itself when it moves between systems? Let's talk JSON.
JSON. Yeah, the universal format, it's great, but it has this hidden trap, especially with numbers.
Right, the precision pitfall. What exactly happens there?
So JSON itself doesn't strictly define number precision. The problem arises when you pass large numbers, specifically large integers, between different systems. Think backend to frontend.
Like from a Java or Python backend to a browser running JavaScript.
Exactly. JavaScript uses I-754 double precision floating point numbers for all its number types. This means it can only safely represent integers up to 253, decimal 1. Anything larger
Loses precision. Gets rounded or changed silently.
Yep, silently. So if you have, say, a 64-bit database ID or a large financial figure that exceeds that limit, by the time it lands in your JavaScript code via JSON, it might not be the same number anymore. And you might not even realize it.
Ouch. So the common workaround is, what? Treat them as strings.
That's the painful industry standard, yeah.
Yeah.
You send those large numeric IDs as strings in the JSON payload, even though semantically they are numbers. It's purely to avoid the JavaScript precision issue. It's a definite gotcha.
Unnecessary evil, maybe. Okay, let's shift gears a bit, move from code pitfalls to people pitfalls. The organizational side. Engineers often tend to view office politics as this dirty thing, right? Something to avoid at all costs. Stay focused on the code.
Yeah, that's a common view, and I think it's a mistake, a big one, actually.
Why? Isn't avoiding the drama and focusing on work more productive?
Look, politics, fundamentally, is just how humans coordinate, how influence works in any group. Avoiding it doesn't make it go away. It just means decisions get made without your input, often by people who understand the tech less.
So avoiding it lets bad politics or just uninformed decisions win.
Pretty much. If the engineers with the best technical understanding aren't willing to engage, to explain the why, to build relationships, then some optimal choices happen. The solution isn't avoidance, it's engaging in good politics.
Okay, define good politics in this context.
It means building trust, understanding what motivates different teams or individuals, what their incentives are, and then communicating effectively to advocate for better technical decisions, better processes, things that lead to better outcomes overall. It's about influence, not manipulation.
Yeah, I can see that. I remember a team, brilliant engineers, built this incredibly resilient system, technically far superior.
Yeah.
But they completely failed to explain why it was better in terms. The finance folks understood the long-term cost savings, the risk reductions. They lost the funding. The technically inferior system won because its proponents told a better story, politically speaking.
That's a classic example. Avoidance meant their technically superior work didn't see the light of day. It ties into another issue, too, the cost of simple distractions and that deep work engineers need.
Right. Especially since, 2020 and the explosion of remote meetings and notifications. How bad is the impact, really?
It's often much worse than managers or even engineers themselves realize. It's not just the 5 minutes the meeting took or the 30 seconds the notification stole.
It's the context switching cost.
Exactly. It's about breaking that flow state, getting back into that deep, focused concentration needed for complex problem solving can take, 20, 30 minutes? Sometimes more. Those little interruptions add up to massive productivity losses.
So protecting that focus time becomes crucial.
Absolutely. Managers really need to actively shield their teams, rethink meeting culture, maybe batch reviews, create dedicated no-interruption blocks. It's essential for getting the high-leverage work done.
Okay, let's shift fully into the AI space now. We've talked a bit about large language models generating code. For a single agent, like maybe using Claude Code or something similar, we hear about context engineering. What's that about?
Right. Context engineering is basically optimizing what you feed the LLM within its limited context window. That's the amount of information it can see at once. It involves crafting good system prompts, giving it the right tools or APIs it can use, managing the message history.
Trying to keep the important stuff in view and avoid context rot.
Exactly. Context rot is when the window fills up with irrelevant older stuff and the LLM loses track of the current goal. Techniques like summarizing past interactions or using subagents try to manage this for single agents.
Okay, makes sense for one agent. But now we're seeing multi-agent systems where different AIs are supposed to collaborate.
Yeah.
Why does basic context engineering kind of fall apart there?
Because it's inherently siloed. Each agent only has its own immediate context window. When you need multiple agents to coordinate on a complex, evolving task, they lack shared understanding. They can pass messages, sure, but they don't have a common persistent memory of the overall state, the history, the shared goals. This lack of shared memory is why many early multi-agent attempts just fail to coordinate effectively.
So they can't just rely on their own short-term memory. They need something bigger,
Yeah.
shared, persistent, like a team needing shared documents or a whiteboard. Is that the idea behind memory engineering?
Precisely. Memory engineering is about designing and building that shared, persistent memory infrastructure for these multi-agent systems. It allows them to build collective knowledge, track progress towards a common goal, learn from each other's actions, and avoid redundant work. It's a huge architectural challenge.
That sounds really complex, way beyond just optimizing a prompt.
Oh, it is. Look at Cognition AI with their AI engineer, Devin. To make that work effectively, they apparently had to invent something called block diff.
Block diff, what's that?
It's reportedly a custom file format they created specifically for taking near-instantaneous snapshots of the virtual machine environment the agent runs in.
Wait, why not use standard VM snapshots?
Too slow. Standard snapshots can take minutes. If your AI agent is rapidly trying things, failing, and needs to roll back its environment constantly, minutes are an eternity. BlockDiff supposedly allows these micro snapshots almost instantly, giving the agent the environmental persistence and rollback capability it needs to operate efficiently. That's the kind of DUP engineering needed now.
Wow, okay, that really illustrates the infrastructure leap. Now let's talk about the output of these AI systems.
Yeah.
The code itself. LLMs are getting good at spitting out code fast. Saves time up front, right?
Yeah.
But what's the catch? What's the hidden cost?
The catch is what we're calling comprehension debt. It's the future pain you incur because the code, while functional, might be incredibly hard for a human developer to understand, debug, maintain, or modify later on.
So the AI writes it, it works, but nobody on the team really understands how or why.
Exactly. It's opaque. You save time initially, but then you spend potentially even more time down the road trying to reverse engineer the AI's logic when you need to fix a bug or add a feature. That initial speed boost gets completely negated. It's like a ticking time bomb embedded in your code base.
That's a sobering thought. If the code itself is becoming potentially harder to understand, how does that change how we should write? Well, comments.
Yeah, it flips the old wisdom on its head. We used to say, good code is self-documenting. Comments are a smell.
Right. Minimize comments, make the code clear.
That calculus changes with LLMs. LLMs rely heavily on comments to understand context and intent. The problem is the comments they generate are often superficial, sometimes just plain wrong, or lacking the crucial why.
So what's the new approach if AI-generated comments aren't reliable?
We need to shift to something like comment-driven development. The idea is that the human engineer writes detailed, context-rich comments first. These comments explain the intent, the constraints, the edge cases, the why behind a piece of logic.
So the comments aren't just explaining code that exists, they're actively guiding the AI in generating the right code.
Exactly. The comments become the primary collaboration tool between the human and the AI. You use detailed comments to steer the LLM towards generating code that is not only functional, but also aligns with the broader architecture and maintainability goals. It's a fundamental shift in how we think about documentation. #tag outro.
What a journey today. Seriously, from the nitty-gritty of CSS ID selectors causing future pain,
The maintenance trap?
to JSON silently mangling your large numbers, the absolute necessity of playing good politics as an engineer,
Yeah, engaging, not avoid it.
and then this massive architectural leap needed for AI agents with memory engineering, plus the looming threat of comprehension debt. It's a lot.
It really connects back to a core truth about software, doesn't it? We're never really done. Software needs constant care maintenance, monitoring, refactoring, eventual rebuilds. It's never static. So if we accept that, and then we look at these powerful AI agents, especially multi-agent systems that generate complex, maybe opaque code, and introduce this comprehension debt, it raises a big question about operational risk, doesn't it?
How so? What's the final thought for people to chew on?
Well, it's tempting to deploy these agents fast, maybe in what some call YOLO mode, low validation, let it run, see what happens, because the productivity boost seems so high.
Yeah, get the value quickly.
But if we know software always needs maintenance, and we know this AI-generated stuff might be particularly hard to maintain, how much ongoing monitoring, how much careful sandboxing, how much extra maintenance effort do we need to budget for up front to make sure these powerful but potentially opaque systems don't just become unmanageable black boxes down the line?
So calculate the true cost, including that future comprehension and maintenance, before you leap. Don't let the fastest code become your most expensive long-term liability.
That's the challenge, I think. Something for everyone to consider as they tackle their next project, especially if AI is involved.
A fantastic point to end on. Thank you so much for walking through all this with us. It's been incredibly insightful.
My pleasure. Lots to think about.
Absolutely. All right, everyone, go forth, write some low specificity CSS, double check those large numbers in your JSON, maybe engage in a bit of good politics, and definitely factor in that comprehension debt. Thanks for tuning in, and we'll talk to you next time.
Spoken Tech for your ears.